Look inside the phone in your pocket, and you'll find billions of microscopic switches etched onto a single piece of silicon. These switches dictate every calculation, every pixel, and every signal your device processes. Orchestrating billions of components introduces a massive engineering hurdle. To function, you have to control the flow of electricity to turn these switches on and off without burning up extra power just to keep them flipped. Earlier transistor designs, like the junction field effect transistor, were inefficient for dense computing. To hold the switch open and allow a signal to pass, they required a continuous flow of control current. It was like trying to keep a door open by constantly leaning your full body weight against it. If you packed billions of those power-hungry switches into a modern processor, the accumulated heat from that wasted energy would literally melt the device. Computing required a switch that could remain open using virtually zero control current. The solution arrived with the metal oxide semiconductor field effect transistor, or MOSFET. The key is in its physical geography. Notice the section directly beneath the top gate terminal. There is a thin layer of silicon dioxide, essentially glass, labeled as the metal oxide insulator. This glass barrier sits right between the control gate and the conductive channel below it. Because glass is an insulator, this layer severs the electrical connection between the gate and the rest of the transistor. The physical gap pushes input resistance into the millions of ohms. As a result, no current actually flows from that control battery, VGS, into the gate itself. Instead of using a flowing current to hold the switch open, the MOSFET uses the static electric field generated by the gate voltage. This glass layer allows the device to toggle high power current while drawing almost no power from the gate itself. Depending on how the materials are layered during manufacturing, MOSFETs are built in one of two base configurations. The enhancement type acts like a normally open switch, blocking current until a gate voltage turns it on. The depletion type is normally closed, allowing current to flow until a gate voltage forces it off. By pairing these normally open and normally closed variants, engineers can construct the interlocking logic gates required for digital computation. To see this in action, look at an enhancement type MOSFET. We start in the cutoff region. When the dial for our gate voltage is set to 0, or anything below the required threshold, there is no physical path connecting the source to the drain. With that path broken, zero current can pass through. The device is in a fully off state, meaning it functions as an open switch regardless of whatever voltage is applied to the drain. But when we dial that gate voltage past the threshold, the static electric field reaches through the glass insulator and pulls charge carriers to the surface. This physically bridges the gap, forming a solid conductive channel. Now that the path exists, we enter the linear or ohmic region. If we apply a voltage across the drain and the source, current begins to flow. And as we increase that drain voltage, the current scales up in a straight, predictable line. Inside the linear region, the gate voltage dictates the channel's conductivity. This converts the device into a precise variable resistor, allowing it to modulate current rather than simply cutting it off. But that linear scaling has a physical limit. What happens if we keep pushing the drain voltage higher? This leads to a phenomenon called pinch-off. In these diagrams, the gray wedge is the depletion region forming near the drain. As the drain voltage increases, this wedge expands, physically squeezing the conductive blue channel until the connection chokes. This chart showing current against voltage illustrates that moment of impact. The straight lines on the left represent our linear region, but once the channel pinches off, the current hits a hard limit. The lines level out into the saturation region. No matter how much higher we push the drain voltage, the output current remains rigidly capped. By reaching this flat line saturation point, the MOSFET locks into its fully on state, acting as a constant current pump. When engineers design a microchip, they are bound by the strict physics of these operational regions. As this linear current equation shows, most variables governing the transistor, like electron mobility and oxide capacitance, are permanently fixed during fabrication. But notice these two variables in the center, W and L, representing the gate's width and length. By altering the physical geometry of the gate on the silicon wafer, a chip designer dictates the exact current each individual MOSFET handles, tailoring each microscopic component for a specific task. This geometric control allows engineers to exploit the MOSFET's dual identity. When slammed rapidly between cutoff and saturation, it behaves as a high-speed digital switch that processes binary data with minimal energy waste. But if they balance the voltage to hover inside the linear transition zone, it acts as a highly sensitive analog amplifier, scaling small input fluctuations into powerful output signals. By enabling both high-speed switching and sensitive amplification in a single architecture, the insulated gate MOSFET provided the physical blueprint for the high-density integrated circuits that power our modern world.